Hi, welcome to MyProjectBazaar.com. Now let me discuss about the title of the project. Our title is Improving Accuracy and Robustness of Self-Tuning Histograms by Subspace Clustering. Actually, Subspace Clustering is a task of detecting all clusters in all subspaces. This means that a point might be a member of multiple clusters. Clustering with high-dimensional data is also nothing but a subspace clustering. In our process, we are going to improve the accuracy and we are going to propose a robustness framework of self-tuning histograms by using sub-clustering method. So self-tuning is nothing but it shares the same problem with the static histograms. They either pick some attributes statically and build the histogram on them, or ignore the issue of locally correlated data by storing full dimensional buckets. Now let me discuss about the abstract of our process. So, query optimization is a function of many relational database management systems. So, the query optimizer attempts to determine the most efficient way to execute a given query by considering the possible query plans. Self-tuning histograms are particularly attractive as an alternative to multidimensional traditional histograms that capture dependencies between attributes but are prohibitively expensive to build and maintain. In this paper, we describe the techniques for initializing and refining self-tuning histograms. In large databases, the amount and the complexity of data calls for data summarization techniques is too critical. So, such summaries are used to assess fast approximate query answering or query optimization. Histograms are a prominent class of model-free data summaries and are widely used in database systems. So-called self-tuning histograms look at query execution results to refine themselves. An assumption with such histograms, which has not been questionized so far, is that they can learn the dataset from scratch, that is, starting with an empty bucket configuration. We show that this is not the case. Self-tuning methods are very sensitive to the initial configuration. Three major problems stem from this. Traditional self-tuning is unable to learn projections of multi-dimensional data. It is sensitive to the order of queries and reaches only local optima with high estimation errors. We show how to improve a self-tuning method significantly by starting with a carefully chosen initial configuration. We propose initialization by dense subspace clusters in projections of the data, which improves both accuracy and robustness of self-tuning. Our experiments on different data sets show that compared to the uninitialized version, the error rate is typically halved. This is the abstract of our process. Now let me discuss about the complete data flow diagram of our process. First, we have to start our process with the data scanning. In the data scanning, we have to scan our data set. If there is there any unwanted data or unwanted symbols found in the data set. So we need to scan the data set. After the data set has been scanned, we have to pre-process the data set. In the pre-processing, here we are, if we are having any unwanted elements or unwanted symbols in the data set, means we have to eliminate that data into the database. After that, we have to partition the data. So in this, we have to partition the data into different data buckets by using regions on the data. So by using that, here we are splitting the data into different buckets. After that, here we are entering into the histogram and cardinality estimation. In that histogram, we have to identify the bucket values. After that, we have to estimate the cardinalities for each and every buckets in the data set. After that, we are entering into the dimensionality reduction. So in the dimensionality reduction, we have to identify the local correlated groups of data within each buckets in the data set. After that, here we are applying a self-tuning and query optimization process. In that, we are applying three mechanisms included in that process, that is minimal bounding, minimum bounded rectangle MBR, and then dimensionality reduction and subspace clustering. These are the main methods in our process. After that, we are evaluating the performance of existing and proposed system by using the parameters of accuracy and robustness. This is a complete data flow diagram of our process. Now let me discuss about the demo of our process. First we have to run title.java in that subspace clustering. So just right click on that frame and click run file. So the title page will be opened here. So this is our title: improving accuracy and robustness of self-tuning histograms by Subspace clustering. So click next button. So here you have to choose our data set, that is our input of our process. So this is our data set. So here we have a lot of data in the data set. After we select the data, we have to scan our data, so it will be embedded into the database. After that, we have to scan. Data are successfully scanned. So here we are applying the pre-process technique for removing the unwanted symbols in the data set. So after the pre-processing has been completed, click next button. So here we can get the original data. Then what are the attributes presented in that data set has been displayed here. After that, we are going to bucketize the data. So this is our data space partitioning, that is called dimensionality reduction. So here we are going to partition the data by using tuples. So just click partition, data space are partitioned. So here we are partitioned into 4 buckets. This is bucket 1, and this is bucket 2, and bucket 3, and bucket 4. So after we partition the data into buckets, here we are estimating the volume of buckets. So here we are calculating the number of tuples in bucket B. Then volume of bucket is a volume of rectangular space occupied, and also for estimating the cardinality. So here we are calculating the estimating the cardinality by using this formula. So here we are estimating the number of tuples in each and every buckets. So after that, by using that, here we are calculating the value for each bucket. Then click next button. Here we are estimating the cardinality. So for each and every buckets, so Q is the query, N of B is the number of tuples in bucket, then volume of Q is the volume of query, and volume of B is the volume of bucket. So by using these type of parameters, here we are going to cardinality, estimate the cardinality value. That is nearly equal to 1. So if the cardinality value lower, if it contains lower, means there is a duplicate number of values occurrences is very low. If there is a higher, means that the cardinality estimation value is higher, means that duplicate values are higher. So here we are estimating that volume of bucket and volume of query. Then here we are estimating the query results based upon the bucket 1. Then here we are estimating the cardinality value. Then click next button. So here we are getting the total dimensions, total data in data set, and the uniformity assumptions in our data. So this is a correlated group of tuples in our data set. So here we have to estimate the correlated group of each and every tuple. So just click button 1, then click medium, then ambience, means based upon these values, here we are estimating the correlated values. Then click next button. Here we retrieve the values based upon the disjoint values on the buckets, then predict results. Then if you are selecting any query, means we can retrieve that approximate results. So this is identifying disjoint values for query optimization. This is for self-tuning and dimensionality reduction. So here just click the self-tuning, means based upon this, here we retrieve the values. After that, here you just click any one bucket, then retrieve results within that bucket. Then here we are going to evaluate the performance by using the false positive ratio. This has been calculated by using bucket size. So this has been calculated. Our false positive ratio value is 0.952. So number of occurrences queried, keyword, total number of words and relevant score is 0.9. So by using this, here we are evaluating our process. Our proposed system is a self-tuning, then self-tuning histogram. Our existing system is a query optimized bucket. So based upon that FPR ratio, here we are evaluating the efficiency of existing system and proposed system by using the parameter called optimization efficiency. This is the complete demo of our project. Thank you for watching.